Co zacząć? Good morning. Today's lecture is going to be on information retrieval and search. After establishing some preliminaries, that is talking about the basic concepts, we will discuss the most popular and probably the most scalable search engine called Lucene, which is packaged into something which is called Solr. So it's a search engine or search library and packaging which allows you to create a service around it. We will also discuss a tool called Look, which allows you both to do searches and to examine the index. The last two topics is an alternative search engine called Indri and the topic of ranking web pages as it used to be done with PageRank. So let's proceed. So there are different examples of search engines. So what you see, obviously, everybody knows Google. Some people know Bing, or maybe everybody knows Bing right now. But the traditional library catalog can also be viewed as a search engine. It's a search engine which is not electronic, unless it was the catalog was transferred into the electronic form. Obviously, the problems of finding a book in a library versus searching something on the internet are somewhat different. Nevertheless, some of the techniques that have been developed for libraries are applicable to web searches. Some others are not. So we have Google, we have Yahoo, we have Bing. We have also something which is called LexisNexis. This is an interesting search engine because it focuses on legal data. So the data is pre-processed, synonyms are expanded, a lot of work is put into proper putting of proper metadata, and as a result, this is probably the most popular a search engine for legal professionals or for any people looking for information on, for instance, real estate transactions or some other legal transactions. Watson could also be viewed as a kind of search engine. Instead of searching using keywords, you search by asking a question, and instead of getting a link to a document, you get an answer. All right, so we talked about Yahoo, which, these search engines operate more or less on the same principles. We do not know exactly how they work because the information about how Google ranks pages is proprietary. We can guess a little bit, and we're probably going to see some of it reflected later in Google patents, so it might be worth checking. Both Bing and Google and also Yahoo allows you to do multimedia search. That means you can search by shape or color, or by look for photographs versus drawings. But there is no good search engine that allows you to exactly describe what kind of image you have in mind and then find it using search. So this connection between visual and text is an open problem. Now we will talk about other systems such as Lucene, which is an open source search engine, and also an open source search engine used as a research vehicle called Lemur and this is sort of the general system, and the INDRI is the search library. So this is the picture for it. Now, these two operate on slightly different principles, and they also have somewhat different query language. That is, questions that you can, the way you asking questions in these two search engines are different. What else can be said? Obviously, Bing, I don't know if you tried, but Google and Bing, for instance, do not admit the same queries. Moreover, the query language changes. So if I am not mistaken, right now it's very difficult to do a real AND query on Google, because the default is that you are doing an OR, and Google is trying to be smarter than you and to give you the results that you do not necessarily want. In many cases this works, but sometimes for technical searches, from my own experience, the results are not, not something I was looking for. All right, so we're going to talk about some of these. So we're going to talk about the old way of doing searches, ranking documents on Google. We will talk about some elements of Watson. We will talk about Lemur, and we will talk about Lucene and Solr. So Bing and Google are not the only ways to search the web. So here I listed a couple of alternatives, so you can read it at your leisure. But it's good to know that that people are trying to do something interesting in this search space, despite the almost complete dominance of the market by the two largest search engines. All right. So what do we do to search? I mean, in order to search, we have to do a couple of things. We have to decide what to index. All right. So make a decision. Are we gonna, index the whole web as Google does? Are we gonna index some collection of documents, for instance, stuff on your desktop, or maybe something in between? For example, we can, I'm working on a project right now where the focus is on patent data. That is, we take the US filings of patents, and we are interested in finding some interesting information there. So for example, we would like to understand better the differences in patent portfolios between companies. An example of that could be, let's take aerospace. Okay, so we have two very big players, namely Boeing in the US and Airbus in Europe. But in addition, we have some other companies, such as intellectual ventures, who buy patent portfolios with the idea of licensing them to other players. So you could imagine a situation in which the position of a company like Boeing depends in part on the patent portfolio that is held by another company, such as intellectual ventures. And so that means that any of the company in this market must take into account what third players are doing. So we would like to offer something like, some analysis of that sort, possibly as a consulting service. But the challenge is, how do we compare patents? The language is very technical, and the techniques developed by computational linguists do not necessarily work best with a very technical language. So this is one challenge. The other challenge is that we really do not know how to how to compare these patents. I mean, what is more important, a description or a collection of claims? How do we connect the collection of claims, which is what the patent really, where the legal value of the patent is, with the description of the invention, which is sort of the setup for stating the claims. So the bottom line is that we need to solve a couple of interesting open problems before we have an interesting search engine to search patents. So anyway, so that was point number one, decide what to index. The second thing would be to collect it. That is, you have to get the data, all right? How do you get the data? Usually you crawl it, all right? There are some tools that allow you to do it, or you can, some tools that allow you to do it sort of relatively easily, or some tools that you program. So I don't know how many of you are familiar with something which is called wget. No. Curl? No. So anyway, so these two tools which are freely available, one is called wget, the other is called curl. They operate basically the same way, allow you to specify the collection of URL and the depth of crawling and a couple of other parameters, and then you just press the button and you create your collection. So once you have it, okay, you have to prepare it, then you index using one of the search libraries. Then the problem is that the collections usually change. So for instance, in these patent examples, every day or at least every week, US Patent Office publishes new patents, okay, both patents and patent applications. So how do we keep it up to date? The good news is that it's freely available, so the only thing we need to do is to run the update. But of course, that means that there has to be some relationship between the old index and the new data. So either you re-index everything, or you create a new index and you do searches on two indices, which sometimes is good, sometimes is not so good. So for example, if you build, okay, in the case of the INDRI search engine, which as we're gonna see depends on the language model for one patent collection might be somewhat different from the language model of the other patent collection. So the searches might not necessarily give you the same results. So anyway, keeping index up to date, and then finally providing some user-friendly search facilities, okay? So you would like, if you're gonna have users for your search engine, you better create some kind of a query facility. So if you look at Google, for instance, it gives you sort of the very simple search window, but then you can modify your searches by specifying dates, by specifying some other parameters. This is perhaps a little bit less user-friendly, but it provides you with, with better query facilities. So there is a trade-off between the two. All right. So again, decide what to index. So we are indexing patent portfolios. All right. For example, this is where we get our data, which is Google actually maintains the collection of US patents. We use Lucene to index. We are keeping it up to date essentially by manual process at the moment, but at some point we're gonna automate it, and then the direction in which we are going with query facilities is that in addition to sort of the standard queries that you're gonna see me doing in a couple of demos in a moment, we also will provide a visual access to the data where you can essentially click on an image and the image somehow represents the topics covered by a patent portfolio, and from that image you can get the documents and you can drill down to the documents. That is joint work with my colleagues in the visualization department. All right, so we already used many of the key terms that I used in information retrieval. So, of course, everybody knows query, document. I mean, these are sort of obvious terms, but in a sense, query is also a document. From the point of view of how a search engine operates, query can be viewed as a usually smaller document. Collection is a set of documents. Sometimes you use the word corpus. Index is a representation, and we're going to describe in a minute what goes into the index. Term is a word or concept that appears in a document or a query. So these are the key terms, just for the sake of establishing the vocabulary. So documents, well, the documents can be pages, images, text. Document can be a reference to a person, reference to a movie. Documents usually have encoding, so it could be Unicode, or it could be ASCII, or it could be something else. Yesterday we saw documents from Reuters represented in an XML format. In Watson we use the TREC format, which is a very simple XML format, you know, document number, title of the document, and text. And well, we already discussed document preprocessing, but we're going to talk about it again in the context of Solr in probably an hour or so. All right. So that's so again. So this is sort of, so far it's all about terminology. So the first important concept in search is the concept of an inverted index. So we have an index which could be you know, something that you have, for instance, at the end of the book. So let's see how an inverted index works. So essentially, an inverted index creates a list of terms and then pointers to where these terms appear in a document. All right, so it points to the document, and usually it points to the location in the document. So if we have two documents, the one says my awesome blog post, and then the second one says my fantastic blog entry, all right, they share some words like my and blog, and they have some words which are different. So therefore, the index entry for blog will have a pointer to the document number 1 or to the first document, and it will also have a pointer to the second document. All right, so that's the basic idea, that you create sort of a list of words with pointers to the documents, and that's what an inverted index is. So let's look at it sort of more mathematically. So this is an example from Wikipedia. We have 3 documents. The first document has strings. It is what it is, all right? Document 2 says what is it, and the third document says it is a banana, okay? I mean, it's a sort of a silly collection of words, but the advantage is that some of them repeat, well, we can use it to explain it. So if we do a simple inverted file index, that is, we're going to do pointers from words such as A to documents, we're going to get a data structure like that. So this could, you know, this could be implemented as a, you know, as a data structure where you have a pointer from the word to the document number. So A appears in document number 2. Banana also appears in document number 2. Is appears in all 3 documents. So we have it here, but also here. We also have it here, and we have it here. And what appears in document number 0 and document number 1. All right, so the concept is relatively clear. And if we do an AND search, okay, with the query, what is it? Yes, what happens is that we take what, which is set 0, 1. We have it here. We take it, or actually is, sorry, which is set 0, 1, 2. And we have it, which is also 0, 1, 2. We do the intersection and we get the document numbers that have all these terms. So essentially we translate a query into a Boolean expression, into a Boolean logic expression, and the end result is a collection of numbers, and these numbers are consecutive, I mean they are document numbers. So, so this is how a simple query could operate on a very simple I'm sorry, on a very simple inverted index. But we can do better than that. As I mentioned before, we can not only note the document in which a word exists, but also the position. So for instance, banana is a 4th word, okay? So it's in the position 3 because this is position starts here. So the word banana is in the third document, yes, 0 document, 1, 2, so 3rd document in the 4th position, and we can represent it as a pair such as this. So now instead of having, you know, sets of numbers, we have sets of pairs of numbers, and the full inverted index looks somewhat more complicated. Of course, I mean, the processing will be done the processing of a query will be done in a very similar fashion. That is, we're going to look for a document in which we can find the words. So that part won't change. What we can do now is we can actually ask for consecutive words. All right, we can do phrasal searches. So if we have a query, what is it? Essentially, the translation of a query is we are looking for a document, okay, so first position X, and then 3 consecutive entries such that X, Y is what? X, Y plus 1 is the word in the set of is, and X, Y plus 2 is in the set of it, all right? So where do we find it? So okay, so we can start with the first set, yes? X, Y is in the set of what? So we have these 2 possibilities, all right? Then we have to look for X and Y plus 1 in the set of is. So if we do here 0, 2, do we have 0, 3 in this set? No, we don't. What about here? 1, 0, do we have 1, 1? Yes, we do. So we have found so far what is, and then what we need to find is it in the position 1, 2. Do we have 1, 2 in it? Yes, we do. All right, so we have 1, 2 in it. All right, because we started with 1, 0, then we found 1, 1, and now we need 1, 2 for the next position corresponding to this guy. All right, so this is how phrasal query operator would work. So this is now the answer is in the bold here. And if we look at our original document, indeed document number 2 is what is it, and it corresponds exactly to the query. So so this explains two things about how to get how to get a document which has particular words, and how to get documents which has a particular phrase. The operators that we can use in this kind of a model is and, or, not, and we can put expressions in parentheses, so we can find banana and not it, all right, banana and it, or is and a, all right. So these are sort of simple queries that we can express in this language. You're gonna see that modern search engines allow you to express much more than that. But before we go there, we need to talk a little bit more about the finding similar documents, because sometimes you cannot find a perfect match. You want to find the best matching document. So the technical term for the model that is most widely used in information retrieval is the vector space model, or sometimes vector model. And the idea is that we represent each document as a collection of vectors, the same way as we saw it yesterday when discussing Bayesian naive Bayes algorithm. So in this case, each document is a point in a multidimensional space. So on this picture, we have 3 terms. So word 1, word 2, word 3. And every document, so for instance, document 2, assuming it is in this plane, has some occurrences of term 3 and some occurrences of term 1. Document 3, which is assuming that it's in this horizontal plane, has occurrences of term 3 and term 2, and document 1, assuming it sort of goes sort of through the middle, has an occurrence of at least one term from all 3 terms. So for example, if we look at it using our previous example, if our terms are is, it, and what it would be somewhere here, what is it is somewhere sort of going at the 45-degree angle from the origin. So now if we represent documents as vectors, the matching of the best match can be viewed as finding, okay, if we have a query Q, the best match can be obtained by finding a document such that the angle between the document and the query is as small as possible. So this is sort of a geometric intuition for search. All right. So assuming that the angle alpha here is smaller than the angle theta, D1 is a better answer to query Q than D2. Notice that, you know, if a document is exactly equivalent to a query, I mean, this angle would be 0 and the match would be perfect. So that's the geometry of information retrieval in this very simple format. And the idea of matching the angles, the degree of match now can be measured by the cosine. Okay, so the cosine has a property that that if the angle is 0, the value is 1. So if you have a perfect match, we say that the query and the document are absolutely similar and the value of similarity is 1. If in some other cases when the document and the query are perpendicular, there is basically no match, and in this case the similarity is 0. All right, so this slide summarizes what we discussed so far. So we have a document space. Matching is done between a document and a query. Distance metrics can be used for match, but you know, distance and similarity are essentially an inverse, and we can talk about it perhaps later when we discuss clustering. The distances that I used are Euclidean distance, Manhattan distance, word overlap, Jacquard coefficient, and some others. And some of them we have explained already, and some of them we will. So for instance, here we have some measures of similarity. So in this case, we have the cosine measure, which is defined as the inner product of two vectors divided by the product of their lengths. Okay, so here this is the coordinate-wise product of x times y. This is the product of their length. So this thing is always smaller than 1. The Jacquard coefficient, we essentially count the number of common items and divide it by the total number of items in X union Y. So again, this would be a measure which would be between 0 and 1. All right, so this would be a good point to, for a digression, and the digressions show an application of what we just seen, that is using this document similarity using the cosine metrics, and also discusses some of the topics that we discussed yesterday. So let's just go through these slides and discuss the problem and the solution that was presented. So the case study here is removing duplicate problem reports. This is the study from the University of Utrecht. The link is provided, so you can read about it if you wish. And the problem can be described as follows, that when you do software engineering, there are always bugs. So the reports about problems or bugs in software are usually written in natural language. Very often, multiple groups test the same product and generate reports about bugs, and therefore it is very likely that some of these reports are very similar, and from the point of view of the software developer, you don't want to sort of to deal with the same thing twice. So you would like to know that once the problem has been solved, all the reports that talk about the same problem have been accounted for. So for that, we need to compare two reports for similarity, but because such reports are written in natural language, they are not amenable to the usual sort of software engineering techniques, and they require natural language processing. So let's look how this is done. All right. So here's a data structure which describes, the table which describes the data structure of a bug report. So what we see here is that such report has a header which is a summary of a problem, something about the project, who was doing the testing, date, how important it is, version of the software that's used, and the description of what went wrong. All right, so some of it is obviously a standard semi-structured or structured data, such as, date of submission could be a structured field if sort of a structure is enforced. Project could have a number, names are probably standardized and not that important for finding similarity. So what we really care about is the summary of the problem, which is in the header, and the description of the problem, because these two things are given in natural language. So the first and the last item in this table is of importance to us. The solution that the authors of this study present essentially takes the standard way of doing natural language processing as described in the book by Manning and Schutze. That is, do tokenization, stemming, remove stop words, do vector space representation, so the stuff that we just heard about, and then do similarity calculation, which would be finding the cosine coefficient between two reports. So the idea is that once we know that a new document is similar to an existing one, the new document can be either ignored or removed. So that is, this is a very, very natural idea. So let's see in an example how this is executed. All right? So it's a very nice example of the process of normalizing the text for either similarity detection or, for instance, the same process would be used to prepare documents for searching. So the original text says the phone crashed when recording continuous audio, then in parentheses if BT is on. So it's something about problems with cell phones. The first step in data preparation is tokenization. Okay, here we just have a collection of just one big string. We have to find elements of that string. So using white space tokenization, we're gonna divide the phone crashes and so on and so forth. But the tokenization process also removes the parentheses and the period. The next step is stemming, that is finding sort of the root of every word in a rough and algorithmic fashion without looking into a dictionary. So crashes get stemmed into crash, okay, so you see the difference here. Recording gets stemmed into record. And I think that's it for stemming. Now, stop words are usually content-free. They are important when we speak, but they are not that important for comparing documents with respect to similarity. So therefore, if we remove stop words, we're gonna remove the, we're gonna remove when, we're gonna remove if, be, and on. All right, so we are left with phone crash record continuous audio BT. this is misspelled, all right? So to get high quality records, you want to replace misspelled words. Okay, so here this misspelling, spelling correction happens after stop words removal. One could argue that perhaps a better place for it could be when you have the original text, because sometimes stop words are suggestive of what the best replacement of the word would be if you want to use sort of a bigger collection, bigger for spelling corrections. But in any case, the spelling is corrected, and now we have the correct spelling of the word continuous. And finally, text normalization, they call it here replacing synonyms, but essentially the idea is to to use one word instead of many synonyms. So BT is synonym for Bluetooth, and therefore BT is replaced by Bluetooth in this record. So as you see, this nicely summarizes the process of data preparation, of text preparation for any language processing that treats a record as a collection of words. So this is treated essentially as a collection of words. And the steps are tokenization, stemming or lemmatization could be used here, stop words removal, spelling correction, which can be done in different places, and then text normalization. So they call it here replacing synonym, but I think normalization is probably a better word for it. All right, so once the text has been prepared, we have a collection of documents. Each document is represented by a record, and then these records can be compared with respect to the angle between them. So for instance, we have a text here, button failure, and here we have button failure and button as a result of removal of stop words and all these corrections. So we have two texts. In one case, button appears twice. In another case, button appears once. So this vector is vector 2, 1. This is vector 1, 1. And we can measure the angle between these two vectors. So this angle is the measure of similarity between these two documents in the vector space. Now, with enough data, a system can create a classifier which says that the two records are similar enough that one of them can be ignored if certain threshold is crossed. So we learned yesterday about creating Bayesian and other classifiers for that. So anyway, this study nicely illustrates some concepts that we discussed so far, such as data preparation and measuring similarity between documents. It also talks about spelling corrections, which is discussed in the book Taming Text, and text normalization, which is they use the term replacing synonyms. But the real solution is somewhat more involved, and I will, together with a copy of the presentation, I will also give you a PDF version of this particular web page that discusses this nice case study. All right. So what we have done so far is we introduced the concept of a vector space of records. We have reviewed some of the data preparation stuff and mentioned the possibility of using a classification to find duplicate records. So now given that we know how documents can be represented in vector space, we have seen how queries can be done in the abstract. Let's talk a little bit about what happens with real search engines. So let's discuss searching using some of the real systems as an example. So first of all, we can notice that in terms of web searches, very often what we find is that web searches contain errors, and now search engines usually allow you, propose a correction even before you agree to that. There could be multiple queries along the same lines, okay? If you get too many Taj Mahal restaurants in Brooklyn, you can put specific zip code for the neighborhood. And, well, there are certainly too many quotes, "Do you love me like you say?" So if somebody looking for lyrics, well, adding the artist might limit the search space. So that's how web query sessions are usually performed, all right? So notice that the queries are often short, there are typos, there is a small number of popular queries and a long tail of infrequent queries, and almost no advanced operators used. Okay, this is all based on keywords. In contrast, in enterprise search, or for instance in the example that that I mentioned before of patent search, almost all queries use advanced operators. You look for certain keywords in the abstract, you look for certain class of patents. You might even look for, for specific companies that own the patents. So there is, the space, there is a big gap in terms of how search is performed between web queries and enterprise queries or technical queries. All right, we're going to review the concepts of precision and recall. We mentioned it before, so here's another example. So the example is a module for recognizing dogs in scenes, identifies 7 dogs in a scene containing 9 dogs and some cats. And so 4 out of the identifications are correct, but 3 are actually cats. So the precision here is that there are 7 dogs in the scene, so we identified 4, so 4 out of 7 is precision, and the recall is 4 out of 9, because we have 9 dogs in a scene. So, so this is, precision and recall. We also discussed the F measure yesterday. So this is, okay, so this is the same picture that you saw yesterday. You count the dots. We are looking for the black dots. So the recall is the proportion of this to that. Precision is the proportion of the black dots to all the dots in the retrieved documents. All right, so that's the intuition. We have talked about it yesterday. We talked about sort of the balance, and the balance is given by this F-score F measure, which is twice precision times recall divided by precision plus recall. It's called, it's called a harmonic mean, and you can see that, it can be generalized to other parameters, but, for 2, we have 1/2 1 over precision, 1 over recall, and this gives us this F1 expression. So this is the mathematics behind it. So what can be said here is that this is when we care about the change, okay? When we so these measures are appropriate for situation when the average of rates is desired. That is, we want to know how fast things change, what the dependence is between precision and recall. If we improve precision by 1%, what happens with the recall? How do we balance the two? There are some variation on the theme. Sometimes we care more about precision, sometimes we care more about recall. So if we want precision to be more important, this number beta, should it be small or large? So let's look at some cases. So if we have beta 0, what do we get? If beta is 0, this is 0, okay, and we have precision times recall divided by recall, so what do we get? Precision. We just get the precision, all right? If beta is 1, what do we get? We get the standard F measure. So if we want put more emphasis on precision, we probably want to decrease the value of beta. There is another measure called the accuracy, which is true positive plus true negative to the total population. That is sometimes useful. Accuracy is something we measured in Watson. So just for the sake of completeness and to mention the term, I'm putting it here on the slide. All right, so let's look at Solar and Lucene. This is a very important package. A lot of enterprise software and web software runs on Apache Lucene. It's a free, open source information retrieval software library. So essentially, it's the basis for a search engine. It's very scalable. It's fast. It's, I would say, relatively easy to use. It is in Java, but there is a port to C# available too. Lucene is an indexing and search library. So this is the core of the search engine. So this is, where you take the document and you create the index, and then if you want to do a query, use a function from the search library to get the documents. It does not contain crawling and HTML parsing functionality. This is given by some other libraries. It is widely used, as I mentioned. So for instance, IBM, Twitter, Akamai, a bunch of others, also a Polish film portal called FilmWeb uses Lucene. There are many other listed at this particular URL. So anyway, I mean, if you're going to learn a search engine library or search engine, Solar Lucene is the place to start, okay? It's basically an industry standard. There is a bunch of related projects which we not going to discuss except for Solar, all right? So web crawling facilities are provided by Apache Notch. In my sort of professional life, I actually never used it. And I was quite happy getting my own data using wget and curl. But you know, if you do some, you know, if you want to have an enterprise recrawling of certain web pages, Apache Nudge could be your choice. Elasticsearch, this is sort of a distributed enterprise search. It's new. It seems to gain popularity. I don't have an experience with that, so I can't really talk about it. Compass is the search engine framework, so if you want to build your own search engine, that's what you use. And there is a multi-platform desktop search application. I haven't used it. I would like to try it at some point. I'm wondering if some of the, you know, some of the commercial desktop search engines actually are using it, but I can't comment too much about that. All right, so we have these elements of a search process. So typically we do a batch indexing, that is, we gather the documents, we index them, and then once the index is ready, a query can be issued, the documents can be found, and then once the documents are found, they should be put in a proper rank. So ranking of documents is important. And then some of these documents should be displayed. So how do you display the documents? Do you display the whole document? Do you display, you know, a snippet of the document? How much of the snippet? All of this is actually debated. Do you cluster the documents that you found, or do you just, you know, give a sample of you know, of the top 5? All right. So before we take a short break, let me just tell you what's going to happen next. So I'm going to show you sort of a demo based on the book Taming Text. All right, and we're going to go through starting of an Apache Solr server, just to show you that this is a relatively easy thing to do. Then creating a search window, and then you know, once we have that, we can add some additional documents to the index and then search these documents. So it's a very, very simple basic demo based on the book. So that's what we're gonna do. Do you wanna do it? Do you want the break now, or shall we do the demo first? Demo first. Okay, so let's do that. All right, so let's go to... All right, let's make it big. All right, so to start the demo, okay, I am issuing the command java -jar start jar. You get a bunch of messages about, you know, the Solr server starting. But the bottom line is, you know, somewhere there in the background, the server is running, and the starting process is really very fast. So let's see, I don't think it's, I mean, we can play it again, just in case you, I mean, it's a very short demo. So essentially, I am using the Taming Text version of the Solr, but if you do it from, you know, one that you download, it's gonna be the same. It's just, so the server, so the first step is essentially, I mean, is starting a server. It always works the same way. The next step, All right, so in the next step, essentially, I am creating a search window. So I'm going to localhost 8983 slash something. I need to, yes, so slash solar, and I get this window. So this essentially, this is the administrator window, which allows me to issue the query. So we're gonna see this this again. So localhost slash solar does the trick, and it tells you that the solar, so basically what it tells you is that somewhere in the background I have a solar server running, so the search engine is there. All right, once we have that, we can submit documents All right, so this is a list of the documents that gonna be indexed, so all the XML files, and I don't know how well visible it is, but all right, let's just let it run. So essentially what I am doing here, I am showing you the top lines of these documents. So, and then afterwards, I am issuing Java post jar command. So I'm essentially posting the XML document, so it's going to be star XML here, to the server. So this is going to create the index of these documents. So these are the files that got indexed. So let's look at these files. And I'm gonna stop it. Okay, so we have here a bunch of XML files. For example, monitor XML, monitor 2, monitor money, solar XML. So all of these are indexed, or will be indexed, but we're gonna look at them first. So I'm issuing a command head -30 of mxml, and we're gonna look at some of them. All right, so what you see there is, okay, let me explain what you see here. Essentially, what you need to do to have the document indexed, you have to tell Lucene two things. You have to tell Lucene that you want to add a document, so therefore you have the bracket add, and somewhere lower would be end of add. Okay, so that is what is needed. The second thing is that Lucene supports fielded search, so you have to specify what data is going to go to what field. So you tell Lucene, for instance, that in the title field, there should be the title of a particular movie, and in the text field, there should be, for instance, a movie review, or you can call that field a review. So here we have a catalog, okay? So we have field name is ID, field name is name, and you know, the ID is something here, twinx 2048-3200 Pro, all right? We have a field called features, and it has something like cast latency with some number, unbuffered heat spreader. So this is like a technical, a description of a technical collection of parts. It also has fields like popularity. So this is important, for instance, if the search is ambiguous, you may want to bring the more popular fields first. And then you also have a field name in stock, which is set to true. So we have a Boolean field here. So again, what you do is you create a document with fields, and you put these brackets, add, end of add, and after that, Solr can be used to submit the document to the search engine. So the whole process is relatively simple. Another comment on that is that, for instance, we have done multiple indices of US patent collection, so we can get the whole patent data, but we index only the fields that we are interested in. Altogether, there is probably over 100 different fields in a patent or a patent application, but for our analysis, we care about 10 of them. That is, we care who the authors are, who the assignees are, that is it owned by Boeing or Airbus, the abstract, the class of the patent, we care about the description of the patent, and we split claims into several fields. So we want claim 1, which is the main claim, in a separate field, claim 2 in a separate field, and then all the other claims also put together into one field. So the format is exactly what you see here, just that the field names are somewhat different, and the process uses direct. It actually doesn't use this particular way of indexing. It uses a different Lucene routine. But the idea is exactly the same. You prepare the data using a program or a script, and then you submit, you post it to the search engine. All right, so what's happening right now in the demo is that these data will be posted. So Java -jar post jar, and the collection of files, which is anything that's XML. Since the files are small, this process is instantaneous, but in general, Lucene is very fast in adding stuff to the index. All right, so let's look at the last part of it, which is querying. All right, so in this Solr administration panel, you have a query interface, so you can find, the query that I issued was $, and you can find documents which have a $, in any of the fields. All right, we can also do fielded search. I don't think I have it in this demo, but we're gonna have it in the demo, in a different demo where we're gonna be doing sort of Lucene fielded search. So that was the query for Euro. As you can see, the interface is very rudimentary and essentially shows that yes, I found the document. And here we have a search for very, and it shows you that here we have a phrase, this document is very shiny. This is a translation of something. Okay. I'm not sure. I think that may be, is it? Yes, that's it. All right. So again, if you look at it, the process is relatively simple. You have a query interface here. You run a query, you check that the query processor actually works by verifying that yes, there is a expression $, in one of the fields. There is another one over there. And similarly for the expression Euro. All right, so this is the query for very. And again, I mean, these videos will be posted together with the rest of the class material. All right, so let's go back to the presentation. All right, so as you can see here, yes, that the whole process is essentially an 8-step process, including changes to, you find the right library, you start the server, you create a browser window. Once you have a browser window, you can investigate what's going to happen. You post documents, and then you query the documents. So altogether, it's a very simple process. There is really not that much mystery to it if your installation, if your system installed properly. All right, let's continue. All right, so this is the summary of the demos that you saw. So starting the server, opening a query window, looking at the data and posting the data, querying the index to see that the stuff was posted. 4 essential steps. So that's another summary of this process. So I already mentioned that, but for the sake of having it all in the slides, how do we get data from the internet? You can use notch, or you can use wget or curl. This allows you, relatively well good control over how you get your data. You can decide that you're going to be very kind and say will not say suck in the whole website within a couple of seconds, but rather do it gently. Once you have the data, you write a script or a program to extract the fields that you are interested in. Then you put the results in the XML file inside the add, end of add bracket, and then you use the postjar command to add a document to the indexes. And something got deleted here. All right, so let's talk a little bit about Lucene query syntax. So before we saw the Boolean syntax, which was relatively simple, and or not and parentheses. Lucene allows you to do fielded search, so you can say that something, the title should have the right way and the text should have go. Lucene also allows you to do wildcard searches, so TE, any character, T or TST followed by any number of characters, so that would be the wildcard search. Now notice that Google doesn't allow you to wildcard searches because these are very expensive. There are just too many possibilities. So, having a wildcard search is more practical with a smaller collection of data. You can do proximity searches, so have Jakarta and Apache within a 10 character or 10 word window. And you can do range searches, so you can look for anything in the title in the alphabetic order between Ada and Carmen. Okay, so anything starting with a B in a title would be a good answer to this particular query. You can boost terms, so you can say that Jakarta is 4 times more important than Apache. You can do also the Boolean thing, and the OR connection is a default connection. So if you type Pink Panther, it is interpreted as a pink or panther. You can do grouping, so you can have, in the title you want a return and Pink Panther as an expression, as a phrase, And we learned just a moment ago about how to do phrasal searches using full index. All right, so maybe now it's a good time for a break. So what we have seen so far is how to put data, how to make sure that the server is running, how to add some additional documents to the server. What we're gonna have in the next demo is looking at the program that takes a query and displays the document. It's written in Java. We're gonna do a quick demo of it based on the book Frankenstein, which comes with the taming text package. All right. So let's see. So 5-minute break. All right. So let's do a 5-minute break. Aha. Dobrze, to zrobimy o 11:20? Dobrze. All right, so let's look at the Lucene query language, and we're gonna do it in a number of very simple demos. And then we're gonna talk a little bit about some other query languages. All right, so let's look at this. All right, so what you see here is the demo of search. I'm running Frankenstein Java, which is essentially a demo program for search. And what it does, it performs Lucene search on the keywords that I am putting here. So the keywords I put here is demon, and it found the grasp of the demon as a string in one of the documents. All right. Here we have the demon whom. It has 2 hits. It displays a bunch of lines here, and the expression that it found is the grasp of a demon whom. Okay, and here we have another demon whom I had seen sent abroad. All right. So far I am doing phrasal searches. So if I look for a phrase demon WH, it doesn't find anything because WH is not a word. So it does. So what we see from this is that it does not do string matching. It actually looks in the index for a phrase. Now, if I type demon whom before, when we search as a phrase, we had 2 hits. This is interpreted as or, so we get 80 hits in total. Okay, so this is a very, simple demo showing the Lucene query using phrasal search and keyword search. So again, the book is Frankenstein by whoever was it, Mary Shelley, whoever wrote it. What you see now is, so we have 15 total hits for demon. Now if we do phrasal search demon whom, we get 2 hits, and it displays the paragraphs that contain the search. next, we verify that this is indeed a phrasal search, the one, the one that we described when talking about full inverse index. Because if we type daemon WH, we get no answers. Similarly for daemon W. Now we verified that the default connection between words is OR. Before we had, I believe, 15 hits for daemon. Now for daemon who, we have 80 hits, which means that it's doing some kind of an OR operation. All right, so let's kill this and let's look at another demo. So here we're gonna look, I believe, at the program itself. Let's see, where is open? Oops. All right, all right, so let's play this. All right, so here we have a display of the program. So this is the program Frankenstein. What you see here is get query expression. It essentially is a loop. As long as, it's an infinite loop from which you can get out by having a null line. It has, it produces the results using the method search. All right, let's see what else can be said here. All right, so this is the structure of the program. So we have we have a searcher, we have a sentence detector, we have finders, we have a tokenizer there. This tokenizer is applied to the query. It is not applied to the text of the book, I believe. So query should be tokenized, then we have some search going on, the results are displayed. So so it's a relatively simple Java program. It can be modified, and if you, the purpose of me showing you this is that it shows how easy it is to work with, to work with Lucene. You can modify it. You can put a different collection of documents or a different document there. You will still run a very similar search query loop. You can examine the results. You can decide which of the results you want to keep. So if we, hold on, if I manage to stop it fast. All right. So for instance, here, originally, oops. No, that's not gonna work. All right, let's just kill it. So anyway, originally, for instance, in this, in this program, it was displaying 20 results, and that was absolutely impossible to put on a screen in a nice way. So I changed the value to 3, and we're gonna see it somewhere in a second. All right. So let's look at this search command here. So top docs, so the documents retrieved, all right. The original value was 20. I changed it to 3. I'm only interested in seeing 3 of them. All right. What else can we say here? All right. There is system prints found, number of hits, and then does the display of the 3 documents that I decided to display. So again, this loop is is a standard look. You can modify it, you can do something else with these documents, you can decide to display only certain fields of the documents once you get the results. All right, let's see. Okay, so let's look at another search. Maybe this one. So here we are looking for the word monstrous, okay. It's somewhat more visible than what we were doing then before. So again, I mean, more monstrous as a phrase gives you 1, as an expression it gives you 129, and that has to do with the fact that more appears 129 times in this particular text. So another verification that the default here is connecting of query terms by or. All right, so let's continue. So the next tool, okay, so we discussed so far Solr, which allows you to create a search server and put the documents into the index. We discussed sort of using Lucene library in this Frankenstein example to retrieve documents and examine them and possibly modify the way, you know, the fields that we want to have displayed. This is a very nice tool which allows you to do two things. It allows you to examine existing Lucene indices, but also allows you to search, all right? So essentially get the documents by directly searching the index. I mean, we are using it very frequently in this patent project that I mentioned before. So this is what you, again, this is an open source tool. It was developed probably by someone in Poland, by a guy named Andrzej Białecki or Bialecki. This is his email. So let's see what is interesting here. All right, so you can do also things which have to do with the index. So you can selectively delete documents from the index. So you found something that doesn't belong there, you can do it. You can optimize the index, so you press the button and some kind of optimization process is gonna happen. Now, this operation is sometimes dangerous because it doesn't always complete in our experience. So if you do that, you may want to have a copy of your index somewhere. All right, so let's go into another demo. So this is running look on patent data. All right, so this is how it looks. All right, I'm doing, okay, I'm going to be doing a query. So the query is airplane. So the default is that the terms are sought in the abstract. What we get here is a collection of documents. So each row is a document, is a patent document. Lucene gives you scores. This is the document ID, which is probably the same as the patent number. There is abstract here, only a few words of which are shown. Assignee, which is who owns the patent. So here is the first two are Israel Aerospace, then we have Boeing, then we have Airbus. We also have some Motorola stuff. There is more stuff from Boeing here, more stuff from Airbus. There is also Alcatel-Lucent at the bottom of it, all right? Here I'm doing another query. Airplane and main classification has the word data. So this is the example of a fielded search. In the field, where do we have main classification, I'm saying that there should be the word data. So all of these, of course, have it because they have data processing. What's happening now is I'm examining one of these documents. So we have an abstract, which is very long. If we try to do it like this, it's really not gonna show. So the best way for this demo is just to do a copy of it and show it in a separate window. No, that's not gonna happen now, but in a minute. All right, so if we put it in the notepad, here we have the text of the patent abstract. So a device for managing a rest period in flight of a pilot in cockpit of an airplane, including parameter acquisition means for acquiring one input parameter characteristic of the desired rest period by the pilot. Yes, this is a very complicated language saying that basically what they are trying to get a patent on is essentially an electronic alarm clock, yes, which would say you put the hour of how much the pilot should rest, and you put it into some kind of an electronic device. I mean, it's somewhat more complicated, so whether this deserves a patent or not depends on what really is claimed in the claim. Is there any originality there? But the gist of it is it's a kind of alarm system for the pilot monitoring the rest periods. All right. So again, let's look at some elements of this demo, possibly stopping somewhere. All right. So the first thing is to work with look, as I said, you need to decide what is the index. So here what you see is that I'm providing a path to the index directory. Okay, so this is the index. It's in my C drive under data Suraj March 25th. So we created some example patent portfolio there. The query that you see in the background is airplane and vehicle and gun, and it has only two answers, but we're gonna look at some other queries. All right, so the index is specified. Now the index is gonna be open. We have a number of documents here. So as you see here, there is about 1.7 million documents in this index, which means, well, so that this is a relatively large collection. Yes, I mean it's not web size, but for a number of documents, it's more than, you know, a person could read or a person could examine just by reading all of them. Let's see. Look provides you with some term counts for each field. So the fields here is abstract text, assignee, city, class, date published, further class, main classification, patent ID, state, subclass, title, type, and kind, of which we mostly care about assignee and the abstract and the class of the patent. All right, there is also stuff, you know, top ranking terms. So type field has the text utility, well, because these are called utility patents, so it's not that surprising. A kind is B2, again, it's a technical term, and then the most popular term in the abstract is the word from. The second most popular is include. So we can look at this and decide, for instance, that none of these should be in the index. I mean, we can put them on the stop word lists. All right, so here comes a query. So I am entering a search expression, which is airplane, making it into a query. Okay, so as you can see, the query is abstract text airplane, and we are getting 378 documents in the answer. And as you see, the results are basically instantaneous, despite the fact that this is running on a laptop and we have 2 million documents there. So now the query changes into airplane main classification data. So we are interested for data processing patents related to airspace industry. And as you see, the query is rewritten by Lucene into plus abstract, which means it has to be there. In abstract text, we need to have an airplane, and then plus main classification is data. So the word and disappears, and it's replaced by a collection of pluses. So plus main classification data. And now we have only 52 documents that mostly deal with data processing. So we have something about helmets mounted. We have a device for managing the rest period. We have some other methods. All right, so the rest of it is essentially examining this particular record. What we see here is that the patent is issued in Toulouse. It has a patent ID with some numbers, has a patent title device for rest management, and it's not a design patent, it's a utility patent. So anyway, the point of this demo was to show that, again, there is this very neat utility called look for examining an index, and in a case where you have a lot of documents, that is probably the best way of examining your collection of documents. All right, so, oops, let's go back a little bit. All right, so the next topic is INDRI, which is another search engine. This search engine is used in Watson. So before we talk about INDRI, I just want to say, show you 2 slides about Watson. So this is the Watson architecture. You have seen this slide before, but I put the yellow background under the stuff that, that is related to search. So this stuff in the middle is the search for evidence. So after we have candidate answers, we create a new search query where we put the candidate answers and the original query term, and we find all documents that talk about the candidate answer and the original Jeopardy question, if there are any, all right? But usually we find quite a few. So this particular search is being done using Lucene search engine. So it has to be fast. I mean, there is a lot of evidence that is being gathered. And in this case, Lucene is appropriate because we are interested in what is basically a Boolean query or a combination of a Boolean and fielded query, all right? What is, okay, so this is Lucene, but this part is not Lucene, all right? This part uses INDRI, and there is a good reason for it, okay? We're gonna go into that when discussing the INDRI search engine. Namely, from, sort of higher level, INDRI search engine creates an index which looks a little bit different than the index created by Lucene, and also the search query process is somewhat different. So let's just look at it. Okay, so this is the process. So essentially the process of search appears twice, first in generation of candidates and then in the retrieval of documents. And then after, after this search is performed, the candidate answers are ranked and the top candidate becomes the answer to the question. Later today, I believe we're going to be talking about how evidence is balanced and combined, what is the mathematics behind it. All right? So we had Lucene, and here we have INDRI. So the two search engines. So now we're going to talk about the INDRI search engine. So it's part of the project called Lemur, developed by, I think, jointly by Carnegie Mellon and University of Massachusetts in Amherst. And as mentioned in the previous slides, Watson used INDRI search to produce candidate answers. So let's look what's happening. So what INDRI does and Lucene didn't do is that in addition to to understanding which document has which word, it also tries to create so-called language model of the complete text, all right? The language model is very much based on the Bayes principle, okay? We're not gonna go into that, but the existence of this language model allows you to find documents which do not necessarily have words, but the words of the query, but the words which are synonyms, okay? So the language model essentially allows you something similar to synonym search for free, just based on the distributions of words. So an example of it would be, let's assume that the query is asking about renal disease, okay, which is a disease of kidneys, okay? So the query has the word renal, yes? But in the documents that are indexed by INDRI, the renal and kidney would be used very much in similar context, yes? So for instance, the drugs for renal diseases would be the same as the drugs for kidney diseases because the two words are synonyms. We do not have necessarily a synonym dictionary, but the fact that the contexts of the word renal and kidneys are the same can be captured in the language model and then used in the process of search. So this fact, the existence of the language model in INDRI was the reason for using INDRI as the first step in search. So essentially, okay, here's sort of the idea behind it, okay, the central idea, which unfortunately we will not go too deeply into. But you can imagine from the probabilistically point of view that once you have a collection of documents, yes, you essentially say that, you know, if I have a document, then the word renal appears 27 times, the word kidney appears, you know, 23 times, yes? So they are possibly in different documents, sometimes they are in the same documents, yes? So now we look at it from the document perspective. So the document, we do not look at the document as a collection of existing words, but let's look at the document as a probability distribution. That is, we think, okay, this document can generate the words that are there with certain probabilities. So a document about diseases of kidneys can generate words renal or kidney, all right? And can generate some other words, names of drugs and that kind of stuff, yes? And so from the point of view of the document, if the document already generated the word kidney, it also with high probability can generate the word renal and vice versa, all right? If the document can generate, you know, the words that appear there and, you know, and generate some, the word collection can also be viewed as belonging with some probabilities to many documents. You can also imagine that, you know, some of these documents can generate query, okay? They can generate a new document called, you know, I don't know, what is the renal disease that whose symptoms are, I don't know, blood in urine, all right? So that would be, you know, that would be the query. So blood in urine and renal would be three elements of the query, and we just model it by the probability of the document generating this particular query. If the document has a high probability of generating the query, then the model says that this is probably the right answer to the query. So this is sort of the reverse of the reasoning that we have seen before, all right? That instead of looking at what document has, we ask the question what it is that the document might have, what it is that the document might be about, all right? So if the document is about kidney diseases, it might be about renal diseases and blood in urine, all right? So this is the mechanics of answering queries in INDRI, which is somewhat different than what we had in Lucene and what we've seen so far in Boolean queries. And our experiments in Watson showed that the results were somewhat better than the results obtained by Lucene. So having a language model was a plus. All right? All right, so that's what, you know, what INDRI does. Again, it's a very nice toolkit. It allows you to index documents in many formats. That is, you know, the simple TREC format, plain text, Microsoft Word, HTML, XML, PDF. I don't know what MBOX is actually. freely available, relatively fast. Another interesting thing about the INDRI query language is that it's very, very expressive. Okay, so we're going to see some examples of the queries, but you can put field restrictions, you can do even evaluation of expressions there, you can do numerical, you can do, since we talk about probabilities, we can do combinations of beliefs, you can do, you know, passages retrieval, and you can get many other parameters from the text. So here are examples, some of the queries permitted by INDRI. So quoted and unquoted terms, ordered windows, so I could say pound OD5 blue and car, which means blue and car should be within the distance of 5, which blue being before the car. This is unordered window. You can put synonyms, so you can say that car and automobile should be treated as synonyms, or in the example that we had before, BT and Bluetooth could be treated as synonyms. You can put some weights on these synonyms, okay? So car being weighted higher than automobile when you rank the results. Types, so any person, all occurrences of person in the field. Restrictions, so dog should be in the title, dog should be in the title or the header. Here we have a more complex query, so within a distance of 1 you should have Trevor and Stroman, so this is names, so the question is there a middle initial or not, and it should be in the title and it should be a person, yes? So in the person field. All right, there are some additional operators such as less, greater, between, equals. So all of this is making INDRI very expressive. Now, so these were how you build simple query terms, yes, and then you can do the combination. The normal combination is combined, so this acts more or less like OR. All right, but it uses the language model, so it's not exactly equivalent to the normal OR. Some more complicated operations related to weighing, summing, negation behaves more or less normally. Maximum of belief of dog and train, so this is, you know, to get numerical estimates and scores. You can put an explicit OR there. You can do field retrieval that we saw in Lucene. You can do passage retrieval, specify, you know, how many words around the query terms you wanna retrieve. You can have requirement or rejection. You can put some priors. You can build query likelihood. You can do query expansion. So, so anyway, I mean, the language is somewhat complex, but it's very expressive. So for instance, if you are building a search engine for medicine, that would be a pretty good way to, you know, to create an efficient and intelligent search engine. So the summary here is that we have a rich query language. We have a deeper document model than simple inverse index. Can take advantage of implicit associations between terms. And the same project also gives you a big collection of web data to experiment with. So essentially you can get it on them from the project on a hard drive. The name of the collection is called ClueWeb. There is more than one of them. All right, so an interesting fact is that when in Watson we experimented with both Lucene and INDRI, Watson creates an abstract query, which is neither in Lucene language nor in INDRI language, and then it gets translated into Lucene and INDRI. So the translation, there is an additional module that does the translation from the Watson abstract query language into the INDRI query language and into a Lucene query language. And it is not sort of a one-to-one translation. It's sort of more of the function that takes the typical query and builds a default INDRI query or a default Lucene query from the Watson abstract query. All right, so the last topic of this segment is PageRank. And since I am supposed to see I'm supposed to have a break at, okay, so we have about less than 30 minutes. We won't finish it, so let's see how far we can go with PageRank. All right, so we have discussed various representations of documents so far, but we have not put any measures on the collections of documents. We have talked about the ranking of the documents with respect to query terms using, for instance, the cosine measure, but this measure is not necessarily appropriate for web documents. So what we're gonna show now is how Google used to rank documents, and probably some measure of PageRank is included in the current Google ranking system, but we of course don't know exactly what is happening there. All right? So PageRank is an example of assigning a weight to a document, and in this case we are not looking into the document itself. All right? So we do not care what words are in the document. We are not trying to classify anything, so there are no train sets, no test sets, there are no vectors of words. The only thing we care about is the structure of the document collection. So we care about the links from one document to another. We can't, okay, so the questions we need to answer is why not simply use binary search when to do the web search, all right? And the answer to that is that there would be just too many results, and it would be impossible to show all of them to the user, and all of these results would fully satisfy the binary query. So some additional ranking mechanism is absolutely necessary. The second question could be, why not use INDRI-like search where users specify precisely what they want? That would be more feasible perhaps from the point of view of getting the user what they want. However, it would be computationally expensive, because the more expressive the language is, the more computational support you need for the query. So Google can't really afford that. All right, so INDRI-like search query is probably not quite feasible on the web. So the answer to the question, what should be the additional factor, comes from the idea that highly cited papers are more important than less cited papers. All right, so citation analysis, And rank is essentially a number of citations with some modifications. The modifications come from the fact that unlike a scientific publishing, not all citation sources are reliable. So for instance, in the patent space where the citations are often assigned by the patent examiner, we can relatively safely say that the more citations a patent has, the more important the patent is, all right? So the ranking there by citation makes some sense. However, on the web, the problem is that you just can't take the number of citations. You have to also look at the structure of such citations. So let's look at the structure of links. So here's what PageRank is all about. So we have a collection of documents, and each document has one or more of incoming links, and originally they are called backlinks. The output of the PageRank algorithm is a numerical score for each document, such that the documents with more backlinks, that is, those that have more quotations, have higher score, provided, you know, these quotations come from highly scored documents, all right? So what is the key phrase here, all right? So numerical score, that would be like citations, all right? That hasn't changed. Document with more backlinks or citations gets higher score, so this is still, you know, the idea of citations. However, what PageRank, the novelty of the PageRank comes from this part, that with more backlinks from highly scored documents, all right? So what we have here is the recursion. To get the numerical score for a document, you have to have scored some other documents before. So there is some kind of a, you know, a recursion going on here, and, you know, we can see it, for instance, in this example. So document A would have a page rank of 0.4, document B would have a page rank of 0.2, document C would have a page rank of 0.4. All right? Now, how do we arrive at this particular assignment of numbers? Well, we're going to discuss some of the algorithms for doing so. All right? This is the figure from the original patent on PageRank, submitted by Larry Page of Google. And let's look at some other stuff that appear in that patent. All right, so this is again a quote from the PageRank patent, which I think is one of the nicest explanation of PageRank, so very readable, I would say, and I will include it with the material of this class. All right. So what is said there is the well-known idea of citation counting is a simple method for determining the importance of a document by counting its number of citations or backlinks. The citation rank of a document which has n backlink pages is simply R of A equals n. So far, very simple. Well, there is actually no mention of the internet in this patent. Here we have, in the case of databases whose content is of a relatively uniform quality and importance, it is valid to assume that highly cited documents should be of greater interest than documents with only one or two citations. Many databases, however, have extreme variation in the quality and importance of documents. In these cases, citation ranking is overly simplistic. For example, citation ranking will give the same rank to the document based cited once on an obscure page as to similar document that's cited once on a well-known and highly respected page, all right? So this is introduction. This essentially explains the idea that, that you have nodes, you have backlinks, you can have forward links, and you can have connections between documents. So this is the figure 1 from the patents, where figure 1 shows a typical relationship between 3 hypertext documents A, B, and C. All right. All right, so this is, the same text, but in a searchable format. And let's just look at how we get from there to the patent. All right, so this is the patent text, all right, and it reads according to the embodiment of the present method of the ranking, the backlinks from different pages are weighted differently and the number of links on each page is normalized, all right. More precisely, the rank of page A is defined according to the present invention as this, okay. So this is the page rank formula, all right. So notice that in order to get a rank of A, we already have to have the rank of pages that link to A. So these are the ranks of the pages that link to A. And what do we do? Essentially what the formula says is the following. Let's ignore alpha for a second, but it says to get the rank of A, get the current rank of B and divide, all the credits by the number of links that B has. So if B points to 20 different web pages, the total rank of B will be divided by this number 20 here. All right, and we do it for B1, we do it for B2, we do it for Bn. So again, if n is the last, if page A is linked to by pages B1, Bn, again, if this rank is 6 and it is distributed among 12 pages, then the total contribution will be 6 divided by 12, which is half, all right? Actually, in this case, this rank can't be that high because what we have here is that this factor will put the rank between 0 and 1. So let's, to change the example, if this rank would be 0.8 and it would be number of outgoing links would be 0, it would be say 10, then the actual contribution would be 0.8. All right, so this is the page ranking formula. There is more than one way of writing it. So the other way of writing it is we still have the alpha factor here, the 1 minus alpha factor here, but we do not have this division by the total number of links. The difference, the order of ranked pages would be the same with the other formula. It's just that in this case, the ranks are between 0 and 1. If you remove the n here, the ranks will be between 0 and n. So the sum of all ranks will be, the sum of all ranks will be n. All right, so here we have an example from Wikipedia. So we have a collection of web pages where the size of the bubble corresponds to to the rank. The ranks are given as a percentage. So the question is whether this formula applies to this picture. So in other words, were these numbers obtained by applying this ranking formula? Well, the answer is yes, because if we sum all the numbers here, we're gonna get 1. So this is, this would be the ranking formula that gives you the values for this particular collection of links. All right, and if we were to use this formula, all right, where we do not divide by n, we would not get 100%, we would get, I don't know, it's 10 here, no, 11, is it 11? Yes, yeah, we would get 11 as the sum of all the ranks. All right, so, so this is the basic idea of page ranking. But notice that we are dealing here essentially with linear equations, okay? What PageRank algorithm is saying is that the sum of all ranks should be 1, all right? There is some initial rank D, all right? And then the ranks are proportional to the links, all right? So essentially, if we have this picture here, yes, the rank of A is the rank of C plus some initial factor, which we put at the beginning, all right, because C is the only thing that links to A. The rank of B is A divided by 2, because A has 2 outgoing links, so it distributes its credit between B and C. So we have 2 links here, therefore we have A divided by 2, and C also puts its credit, C puts all the credit into, is it correct? C puts all the credit, or maybe, no, I think that would be outgoing here. No, I think this is the wrong picture here, I'm sorry. C would have, no, I'm sorry, this is fine. C gets the credit, okay? C gets the credit from A, so half of the credit from A, and it gets the credit from B, so this is right, okay? And gives all the credit to A, which was accounted for here. So yeah, so this is the correct correspondence of the picture and the equation. So now we have, we have a collection of 4 equations and 4 variables. We can solve it, and we can get, for instance, that the rank of A is 2 over 5, which is 0.4, which is exactly the rank that it's supposed to have. So typically in a system like that, if it doesn't have, self-looping, we will get a system of equation with the same number of unknowns as equations, and such systems have typically unique solutions. So we can solve these, we can find ranks of simple graphs like that relatively easily just by solving linear equations. All right, so this is essentially a computation using a different method, okay? So here we are using the rank computation where we do not divide by the number of nodes in the graph, and therefore the final value of the rank is 6/5, all right? So the equations that we have here is AB plus C is equal 3, all right? So the total credit is equal to the total number of nodes. We have the same graph, so the equations haven't changed. Once we solve these equations, we are getting the value of page rank being equal to 6/5, so 1.2. So couple of comments on that. There is more than one way of doing it, as you saw it. There is more than one way of computing and page rank, and we're gonna perhaps discuss some of them. But I want to point out that currently Google ranks are above 1, so they do not exactly correspond to probabilities. Originally, as in the patent, the ranks were between 0 and 1. What is the exact formula that they use? I have no idea. I'm pretty sure that it's more complicated than what I am showing, that what I am showing here. Nevertheless, giving credit to highly ranked sites, I'm pretty sure is part of the formula. All right, so here is another example, computation. So here we have page A, which is linked to and has a link to page B. Similarly, it links to and has a link from page C. So this is the graph. We are using the formula where the total rank, sum of ranks is the number of nodes. So what do we have? A gets the credit from C and B, and both B and C get half of the credit of A. From that, we do a substitution to the equation, and we get the rank of this particular node to be 3/2. This particular example is taken from the book Fundamentals of Predictive Text Mining, and in the book it is computed by an iterative process. What I am showing here is that you can get a very similar results by solving linear equations. So the question is, if you translate a graph like that into a system of linear equations, could such system be contradictory? The answer is yes, but typically it would require some self-looping. So a node would point to itself. This kind of stuff can introduce contradictions in the system of linear equations. All right, let's see. All right, so Python has facilities for computing page rank. All right, so using this particular formula, so 1/d times, and here we have this page ranks divided by the number of links. Usually these numbers are said that this number is 85, this one is 15. Sometimes, I worked also with 0.9 here, 0.1 here. So you will get different convergence rates depending on what you put there. The algorithm converges relatively fast. So for instance, I ran some experiment on patent data, so patent citations, and using about a collection about 3 million patents and their citations, so it's a relatively large collection, you get the convergence within less than 20 steps. All right, so doing it by iteration is, what you do is, well, you put the damping factor here, yes, and then you just look at, the nodes. So we have the node. So if we compute the rank of A, we care about B and C. So what do we get from B? From B, we get half of the initial value, which is 1. And from C, we get a full initial value. All right, so altogether by substitution, we get 1.4. All right, for B, B has only one vector pointing to it that's come from A, so it gets full credit from A, so it will remain having the value of 1. C, on the other hand, gets only half of the credit of B, so it ends up the first round of iteration with the value 575, all right? So in round 2, we start with these values, and now, after these adjustments, again, we're gonna divide by 2. So we have B was 1, so we have 1/2, C was 575, so altogether this gives us a smaller number here. The rank of B has increased, the rank of C remained the same. After round 3, we see that the rank of A increased, the rank of B decreased, and the rank of C also somehow increased. So a couple of more iterations would give you the final numbers, or you can solve a set of equations and it's also going to give you something similar. Not exactly the same, but similar. All right, Wikipedia has more stuff on PageRank computation. So we presented here the computing rank by iteration. All right, there are some variations on the theme. So for instance, instead of doing it 3 ranks at a time as we saw here, we could substitute the subsequent values into the next equation, and this also works reasonably well. Solving linear equations can be generalized into multiplication of matrices, and that is also explained in the Wikipedia article. It's not necessarily a very readable article, but it should give you some idea about what actually can be done when the graphs are bigger than what we are putting here on the slides. All right. So the summary of what we talked about is that the key concept to understand is the fully inverted index, because that's used by all search engines. To understand how web search engine works, you have to have the idea about the PageRank, vector model for representing terms and documents. This is essentially the repetition of what we discussed yesterday in terms of term document matrix. The variation on the theme that came today was sort of using the cosine similarity to represent the matching of the query with the document. We discussed different retrieval models, all right, and obviously Boolean retrieval is at the core of IR, but you saw that the languages can be very expressive. We discussed Lucene and Indri. We talked about Look, a way to explore the index. Let's see what else can be said here. So I think that pretty much summarizes what you need to know about information retrieval. And I think we're gonna have a longer break now. Since I'm supposed to see the rector, so let's meet in about 25 minutes, or maybe even 30 minutes, just in case. All right, I will take this with me. A little bit more than 1% about a movie, okay? another 1% about the state, and then as we go along, I mean, this goes on and on and on. So the strategy that we should be able to identify in text in advance all the entities that are relevant to Jeopardy questions would not work, all right? So something else had to be done. We could identify perhaps some of these, you know, the most popular, and that would be helpful, but in general, this machine learning approach that we described a moment ago would not work. So what replaced this method, okay? So what replaced this method is called deferred type evaluation, all right? So essentially decide whether something is a person or a city when you have all the information that's available about this particular string, all right? So let's look at some examples. So in question answering, questions about people usually have some other attributes and relations. So for instance, we can ask about the oldest person to swim the English Channel, all right? So we are not looking for just a person, we have some other attributes, some relations, swimming the English Channel and being the oldest among the people that are recorded somewhere in the database as the ones that managed to get from France to the UK or vice versa. So how do we find the oldest person to swim the English Channel? Well, we can look in text. So here we have, you know, some texts that come in the research about, you know, oldest person swimming the English Channel. All right, so here we have Lynn Cox on July 1972 at the age of 15 breaking both men's and women's records. So oldest and record could coincide. So I mean, it's a reasonable search result. We have some other entities here. All right, so here we have Marlene Bell at the age of 17, all right? I mean, this is not exactly the oldest person. Nevertheless, here we have crossing from France to England, okay? And there is some, you know, time given here. And the word person appears here. We don't have the oldest, but we have the youngest. So we have to know that, you know, that oldest and youngest are typically not the same. Here we have another example where we don't have oldest, but we have aged 70. Well, would this be somewhat related? All right. We don't know. We need some evaluation. Here we have the oldest male swimmer to cross under the rules of Channel Swimming Association is Australian Clifford Butt, who was 67 when he crossed, okay? So we don't have that, you know, there is no word swim, we have the word cross, but we have the word swimmer here, so can we relate this stuff? So as you see, the information is not explicit, yes? It requires some reasoning capability, or at least, you know, some guessing capability in order to, you know, to make sense out of these examples. So obviously, Watson does not have human reasoning capabilities. So instead, Watson has a collection of scorers which essentially will try to find whether, you know, what is the correspondence between the entities mentioned in the query and the entities mentioned and the relationships mentioned in these examples. All right. So here we have another piece of text. All right. Here we have, you know, oldest person to swim the English Channel. So this is a pretty good text. And we have the age of 70, all right? So while the other text comes, say, from Wikipedia, this piece of text came from the web, all right? So what is the problem? The problem is that the web information is not necessarily reliable. So again, even though this is a pretty good answer to the query, we don't know if this is true. This has never been, you know, confirmed by any authority. So what, you know, the Watson's scoring method also included sort of weighing the value of the source. So say Wikipedia or some other encyclopedias were more important for scoring than the data that we got from the web, because the web data has many contradictions, even though, you know, this is a perfectly good segment. So we have some other text, all right? So we have, all right, I think that's the text we saw before, yes? So we have here oldest person to swim the English Channel, and here we have the oldest person to swim the English Channel was Clifford Butt, okay? So now we have a problem because both of these texts claim that, you know, that they are about a person, the oldest person who swam the English Channel. So how do we decide which of them is really true? And there is, you know, there is no foolproof method, but essentially what Watson does is it creates a collection of scores, and then these scores determine the coreference between the oldest person to swim the English Channel and the name of the person. And this is done after all evidence is assembled. So essentially, if we go back to this example, yes, we're gonna have, say, two candidate answers, Roger Alsop and Clifford Butt, all documents that mention English Channel or swimming the English Channel or are somehow related to swimming an English Channel, and Clifford Butt will be put in one bucket of documents. Similarly, for Roger Alsop, all these documents, the supporting passages, will be put in another bucket, and then a collection of a few hundred scorers will create a collection of numbers, so about 400 numbers, that talk about different aspects of how the query is related to any of these segments of text. We're going to get the final score, and more likely than not, we're going to get the right answer. But we're going to get the right answer only with very high probability. Okay, so this is what we mean by deferred type evaluation. We do not know whether this is, you know, whether we have found the oldest person to swim the English Channel. We don't even know that we have found the person until we gathered all the available information and we weigh this information using a collection of scorers. All right, so we have seen this example before, but essentially this is the same process. That is, we have a query finding, you know, finding a city in which C.W. Post created a warm cereal drink called Postum in 1894. We find the relations of interests, and we have a bunch of keywords. We find candidate answers. We find supporting passages, so evidence, and then we get a bunch of numbers, and at the end, these numbers are converted into probabilities. So in this case, we get the probability score of 85. So notice, I mean, that these are similar numbers. So, you know, these look like numbers that we were getting when doing named entity recognition. And the process of conversion is the same, and we're going to explain it in a minute or two. So how do we get from a list of numbers to probabilities? So first of all, I mean, there is a way of reformulating naive Bayes as a linear scoring exercise, all right? So, even this multiplication that we have seen in the naive Bayes algorithm can be viewed as addition of certain other numbers, and I'm going to show the formula, I believe, in the next slide. And then the next step, okay, is the translation of such linear score into probabilities, and the function that does it is called the logistic regression function. So let's look at it in detail, all right? So we're not going to go into the detail of this formula, but essentially what you see here, this is a way of reformulating the naive Bayes formula, okay? So probability of a document being in class C is given by the probability of a class times the probability of the class generating the elements of the document, all right, divided by the probability of the document. This can be, since x can be 0 or 1, this neatly corresponds to the Bayes formula. So I mean, so we can leave it as an exercise, but basically depending on whether x is 0 or 1, you will get the right weight of the right formula for the naive Bayes algorithm. Now, by taking the logarithms of this, we can transform this expression into this kind of expression. So 1 over probability of x, and here we have essentially a linear function. This is the bias that we have seen in the method for named entity recognition, and here we have the sum of weights. X1 through xn are zeros or ones. So we are summing weights exactly the same way as we were summing weights when recognizing a person, all right? So this is the connection, okay, that this linear recognizer that we use in named entity recognition has a close connection to the naive Bayes algorithm. And, the weights are given by these formulas, and the bias can be computed as, as a constant based on this summation, all right? So anyway, we do not have time to sort of to do the full mathematics behind it, but it's certainly accessible to any of you. The only thing that you have to know here is that these numbers are zeros of ones, and depending on whether you substitute 0 or 1, you will get a different version of it, and that corresponds exactly to the naive Bayes formulation. Coming from here to here is just the question of logarithms, and these expressions should guide you here, all right? So, all right, so we have the connection between naive Bayes and adding, and what we would like to go, where we would like to go now is to go back from adding of numbers to assignment of probabilities, all right? So let's look first at scoring, all right? So if we want to score whether a document is in a certain class, all right, for instance, in the class earning, we could simply use the linear model that we have seen here. That is, we can just look at this thing, yes? We can add these weights and a bias and create a score. So for instance, if we have a document which has dividend payout and rows, okay, as as the words, okay, so this would be the words in our dictionary which appear in the document and other words are ignored. What we do is we look at dividend, okay, it has the weight 0.87. We have payout, which has 0.6, so this altogether gives us something like 1.4 something, and then we have rows, which subtracts a tiny bit, so we get the final score 1.46. So it's positive, so it's suggestive that maybe this is about earnings, yes? So what we have here is that all words in dictionary have a score, and a new document we treat it as a bag of words and assign a score in a way that we just did, all right? And the positive score is suggestive of, you know, of being in the class. Negative would be suggestive of not being in the class. So the advantages of this is the representation is very simple. We are adding numbers, okay? The computers are very good at it. The computation is simple. The computer can add many, many numbers very, very fast, yes? It is a generalization of naive Bayes. The problem is we don't know what to think of 1.4. We don't know what to think of 5.6 when doing named entity recognition. So we need a way to go from this simple computation model into probabilities. We would like to know that, you know, that the probability of the document being an earning document is, say, 45%, and probability of a string being a person is, say, 75%. So how do we do that? All right, so here's a function called the logistic regression function, which maps the straight line from -infinity to infinity into the interval 0, 1, all right? And for 0, the value is 0.5, so we don't know what to think of it, yes? I mean, this would be, it's a 50-50 chance that something is a person or is not a person. So have you seen this function before? The logistic regression? No, okay. So let me explain it. So now if we have a linear score of -4, we can translate it into a very low probability. If we have in this function a linear score of 3, it would be a very high probability, all right? Okay, the general form of the function is this, that we have a bias here. Here we have a linear expression, so a weight times the presence or absence of the feature. And at the bottom we have a similar expression, all right? So we can formulate it in one way or another. All right, so what do we need to know about it? All right, well, if we have a mapping into the interval 0, 1, it means that we are dealing at the end with probabilities. Another thing is that the same function works not just for adding two terms, but also if this multiplication is actually a bigger sum. So if this is a inner product in many dimensions. So this is going to work exactly the same way, and we're going to illustrate it in a second with a real example. Oh, another thing that I have here on the slide is that logistic regression was the most reliable scoring function in Watson. So at the end, you know, when we were trying to decide whether to answer the question, yes, I mean, we had to put some score on the candidate answers. And we experimented with many different scoring functions, purely linear scores with some threshold, for instance. But it turned out that logistic regression was giving us the most, most reliable results at, the threshold that we chose, which was 0.7. All right. So here is a logistic regression in more than one dimension. Okay. So here we have a surface, and the process that's modeled by a logistic regression is not answering questions, but it models the probability of cell death as a function of toxin concentration and time. All right, so we have two axes here. One is time, all right, in hours. So this goes this way. Here we have the toxin concentration. And, well, naturally, if we have a very high toxin concentration and a long time, I mean, the probability should be 100%, yes? So that is not surprising. So what we have here is that we are modeling the process that if we have sort of medium concentration, then the probability after 250 hours is very high, but essentially it grows along this curve, yes? Similarly, if, for a fixed time, the probability of cell death increases as the concentration of toxin increases, all right? How was this surface derived? It was derived by observations. That is, what researchers did was put some poison into a cell at different times and derived some points in this space. And then the model that they chose, which is the logistic regression model, was essentially trying to fit as well as possible the points that they found experimentally. So the point could have been somewhere here, another point could have been somewhere there, yet another there, yet another there, some points here. They do not necessarily, the points that were found experimentally in an experiment were not necessarily on this surface, but the point is that the surface was the best match for the results of experiments. All right, so what logistic regression gives us is it gives us the ability of aggregating influence of multiple factors on a variable. So this is very much what's happening in language processing. There are multiple factors that determine whether some expression refers to a person or a company. So McCann could be a name of the person, and it could be a name of the company. So one factor that determines it is that that you have a capital letter and it looks like a name. Yes, we could write a regular expression for that. The other factor is position in a sentence. The other factor is other words near it. Yes, so if it's preceded by the CEO of, and then you have McCann, then McCann is more likely to be the name of a company than the name of the person. So aggregating influence of many features on the variable, on the decision variable, which is it a person or not a person, is done very nicely using this logistic regression function. So, all right, so, well, we can read from this model certain things, like we can read that, a concentration of 150 at time 50 kills about 30% of the cells. So we have here, all right, so this is where this point would be. So this is what the model predicts, all right? We do not necessarily know it from the experiment, but based on other experiments and based on this model, this is what we can predict. So as I said before, essentially this logistic surface here is the best fitting surface, and best fitting means minimizes the average sum of errors, of experimental errors. So how was logistic regression used in Watson? All right, so we mentioned already the main task, that is predicting the probability that the candidate answer is correct. The logistic regression there had 550 features. All right, so it was a relatively complex and difficult to learn logistic function, but the idea was the same as what we discussed a moment ago, the relationship between probability of cell death and the Poisson concentration and time. So the results here was winning the game. We also used logistic regression to decide whether the data that we gathered from the web is likely to be relevant for answering questions, all right? So in this case, we had only 12 features, which I'm going to show on the next slide, and the task was we were taking a snippet of the text from the web, and we wanted to understand whether it is relevant to a particular topic. So for instance, you know, a Wikipedia article about Poland, yes? There is quite a bit of stuff on the web about Poland, and we would like to know that, you know, that the snippet that we grabbed is useful. So how do we know that something is useful? Well, it should be relevant to the topic, and we can measure it by, for instance, a number of words that overlap. Another thing is it shouldn't be a complete overlap, because it's likely that it's, you know, it could be simply a quote from Wikipedia, so it would be redundant. It should come possibly from a more reputable source. So we were trying to weigh several such factors, so 12 features, and again, logistic regression trained on a sample data was used to decide, you know, which snippets we're gonna keep. The result here was about 4% gain in accuracy on Jeopardy questions. So this was important because up to the end, we were not sure that we could actually win against the human opponents. All right, so this is the list of features that were used in logistic regression. So overlap of the topic, certain TF-IDF scores. We didn't talk about it yet, but we're going to talk about TF-IDF tomorrow. Titles, okay, so how many title tokens appear in the particular nugget or snippet. Pronoun, existing person pronoun, third person pronouns were somewhat predictive of quality of nuggets. The position in search, all right, so we were getting our nuggets by going to Yahoo through their Yahoo interface and getting about, I think, 1,000 URLs per query. After that, we would be using wget or curl to get the actual data. And one of the important features here was the document rank in search. So more highly ranked web pages were more likely to have snippets or nuggets of high value. The length of the nugget was predictive, with very short nuggets being not very good and very long nuggets being not very good. So that kind of stuff, okay, was, so these are very complex features, and obviously it would be very difficult for a human to decide which of these are more important and how important they should be. So therefore, machine learning was used and the information was aggregated using logistic regression. So how do we get the features? Well, as in this example about toxins, I mean, the experts decide what is worth modeling. So they suggest features, and then the machine either confirms the features. So if the model works very well, that means this is the right collection of features. All right. So for instance, in the model, in the toxin model, the features that were used was time and toxin concentration. But you could imagine that our features could be more important. Like, for instance, temperature, yes? So maybe time was less important than temperature, okay? So depending on the model, on the features that you choose, you're gonna get different models, and some of these models gonna work better, some of them gonna work not so good. So you need some domain expertise to choose among many, many possible features. You need 10 times more data points than you have features. So for instance, to answer Jeopardy questions, we had about 550 features. So that means that you need a data set of at least 5,000 Jeopardy questions with answers and with supporting evidence in order to have a reasonable approximation of a model. Another thing about logistic regression, besides this mapping of linear data into probabilities, is that it can help you eliminate redundant features, because what's going to happen is that the features which do not contribute much will gonna get low weights, all right? And that way you may want to consider eliminating them and possibly replacing them by some other features. All right, so logistic regression is a good model for learning a classifier that produces a probability score. And usually that happens when we have quite a few features. It's probably one of the best models, and if you ever work with machine learning, it's definitely something to consider. It's not as easily trainable as naive Bayes, but very often it's going to give you somewhat better results. So, you know, start with naive Bayes, see if it performs to your liking, but if it doesn't, try to create a better model and use logistic regression. All right, so this will be it for today. If you have any questions, let's discuss it. What do you need to know for the final exam? All right, so most likely the final exam will have something about logistic regression and named entity recognition. So the format would probably be as follows, that I'm going to give you a table, all right, with some weights, and I'm going to ask you, okay, which of the entities mentioned in the text would be classified as, say, persons, all right? That would be a natural question. There could also be a question about cosine similarity. That is, you have a vector and you have a query and a collection of documents in a space, and you try to find the document which is most similar using the cosine similarity method. It's possible, but I would say that the question about named entity recognition and regression is definitely more likely, all right? Because I think this is an important topic. It summarizes two concepts which are both very important. One is doing named entity recognition, and 2 is applying the mathematical model that is logistic regression. So I view both of these as very important. So I'm pretty sure something like that is going to happen, is going to appear on the exam. Let's see, what else did we talk about today? We talked about search engines. I don't think there will be anything mathematical there, but there could be a question, you know, about, I don't know, just give me a name of a couple of search engines, or describe, you know, possible variations on the query language, yes? I mean, something like that. Just think about, you know, what search engines do and how they do it, and you're gonna be fine. So we talked about search, we talked about logistics. Yeah, so that's it. I think, I mean, if you go through this search material, just read it and try to understand it. And if you go through the named entity recognition example and do something similar on your own, I believe you're going to be fine at the exam. So to finish, you want the material, yes? Yes. So please give me 10 minutes and I will take a look at some of the stuff, then convert it into PDF and give it all to you.